Physics by example, problem 5. The experimental values in table 3 were obtained for the Young modulus E and the shear modulus G of steel. Table 3. E divide 10 to the power 10 newtons per meter squared, 21.1, 21.0, 20.09, 20.06. G divide 10 to the power 10 newtons per meter squared, 8.12, 8.15, 8.13, 8.08. So off the bat it looks a little correlated. Find the formula E divide 2G minus 1 equals nu was then used to calculate the Poisson ratio nu. Find nu and estimate its error. So let's go to the solution. If the errors in E and G are uncorrelated, we should be able to obtain equally valid results by calculating the average of the Young modulus divided by 2 times the average of the shear modulus minus 1. And nu equals everything averaged, where x averaged, or mean of x, is the mean value of x. As a check, we will try both methods. Method 1, working with units of 10 to the power 10 newtons per meter squared, calculate E, the mean of E. So we just add them up, divide by how many elements there were, and we get 20.9. Now we want to work out Young's modulus squared and the average of that. We go back to the table, we square each of these values, and then we divide by 4. And this is used to calculate the variance. So in the equation for the sample variance is the difference between the squared mean and the mean squared, all square rooted. And we get to having this one squared, 20.9 squared. Oh yeah, I should have used the of different notation. Would have been better than this symbol for square root, but it's fine. And this 368.45. So 436.845 minus the square of 20.9. All square rooted. Just to make that extra clear, gives us, we get a value of 0.919 for the variance, simple variance. So we can use that to calculate the error. The error in the mean of Young's modulus is thus 0.19 divided by root of 3. So where does this square root of divide by square root of 3 come from? Well, statisticians and sometimes physicists are evil. And we have a formula here for the sample variance, defined as this formula here. Whereas in another textbook or another source, we would say the sample variance is characterized by exactly the same formula as the population variance, but instead we have 1 minus the number of readings we took. So that's where it would turn into 1 divided by 3, and then we would square root that. But these are two conflicting sources. So this is the formula used in the book. So the sample variance is defined as this formula here, the sum of this, and the standard deviation of the sample, the best estimate of the standard deviation in the mean is sigma m approximately equal to the square root of that sample variance divided by square root of n minus 1, and the result of n measurements is quoted as the mean of the measurement plus or minus this standard deviation of the mean. So let's use the formula in the book. I'll just also include the rest of the formulas given in the book here for future reference, and we can return to any others that we need to. Putting this all together, we get 0.19 divided the square root of 3 equals 0.11, and we work out the fractional error, which is denoted, well, we get this symbol, and we divide it by the mean, and we come out with 0.5%. We do a similar method, exactly the same, but for G. The mean of G, 8.02. Fractional error on the mean is 0.2%. Combining these into that formula given, we get average meanie divide 2 mean G equals 0.287 plus or minus 0.5%, and we get that as a value 0.287 plus or minus 0.006. So nu equals 0.287 plus or minus, well, I think that's a mistype there. Oh, yeah, maybe with the, 0.006. Sorry, yeah, to trip up, because the minus 1 is in that formula as well, which I forgot. So recall that we had two possible methods for calculating the error for nu for this formula. One is the case if they were uncorrelated, then we can treat these error values as separate, and the second one was if they're connected, if E and G were connected in terms of their error, which we don't know actually because we don't know about the experimental setup. So we get down to method 2. Calculate Young's modulus divided by 2 times the shear modulus minus 1 for each set of table values, table 4. So these were the values we were originally given, and then we plug in this, divide 2 times that minus 1, we get these values. Evaluating the mean value of the quantity and of its square as before. So this time we just do it on this thing, so we just get this plus that plus that plus that, divide by 4, and we square each of those values, and then we calculate the error in the same way as we did before, and we arrive at 0.005 as being the fractional error, and then the percentage error would be that divided by that. And we say this value is not significantly different from method 1, so we are justified in assuming that the errors E and G are uncorrelated. So you could do a kind of a test on those values if you had more samples from different materials, I guess, as well. Yeah, so I think next time go through the video again and try to calculate it from scratch with a calculator, or pause this one intermittently.